think we're completing the topic on log amplifiers. We're completing the topic on log amplifiers. And Sierra Ramon is seeing 38 of you at rest.
They'll be joining in. I think they're just late.
Okay. So in the last class, I showed you a log amplifier, a practical log amplifier, or the type that you can do in the lab and get results. And we said that in the derivation of that last practical log amplifier, which we were able to calibrate, we found that we had to make some approximation. We had to make some approximation in the determination of the current of the transistor to the right. It means the transistor next to op-amp A2 in this one, in this circuit over here. So this is a modification of the earlier circuit where we had to approximate that IC2 is VR divided by, there was a resistor going to VCC. So it was VR divided by that resistance. But now in this circuit, we've changed that resistance to this circuit over here where we have the R5 and the op-amp A3. So with this circuit now, we no longer require an approximation. So this is called the improved multi-transistor log amp. Improved multi-transistor practical log amp. It is practical because you can see towards the input, we have your null offsetting potentiometer, which you're calling P1, with the value 100K, going to the 100 mega to the 10 mega ohm, and to null offset the output op-amp A2. We also have a similar circuit, which are calling potentiometer P2 here, with this 100 mega ohm. So this is to ensure that the output of the op-amps are 0 if the differential input voltage is equal to 0. Now let's show that this circuit can compute the log of a voltage Vs. So to analyze this, I can start at point A over here. Point A, these diodes D1 and D2 are for protection. And this reminds me, in the labs, you people are going to blow lots of op-amps if you don't have these protection diodes in your circuits. So these diodes D1 and D2 are protection diodes to ensure that we don't reverse bias the base emitter junction beyond the limit. So they don't come into the computation. So if you apply KVL starting at point A, point B, point C, I can write an equation minus VBE1 If I call this transistor here Q1, and let's call this one Q2. So the corresponding base voltages will be VB1. So if I start at point A, write an equation minus VBE1 plus VB2 should be equal to the potential at the positive input over here. And this potential should be equal to this arbitrary voltage V. So V just an arbitrary voltage I'm going to be using. Okay. So let's start the analysis. If we assume that we know this voltage V, this arbitrary voltage V at this point over here, then V plus the voltage drop across R3 should equal to V naught. So if I take this part over here, I'll get a potential V plus, I'll call that current which is passing to create this VI into R3 should be equal to V naught, where I is equal to V divided by I is equal to V divided by RT plus R4. So that's the equation I'll start with to simplify things. So let's assume an arbitrary voltage V at the inverting input of A2. So V plus the drop across R3 should give us our output voltage. But if potential at the inverting input of A2 is V, then a current equivalent to V divided by RT plus R4 must flow through this RT plus R4. So this first equation here, I can write it as V plus V divided by RT plus R4 in R3 to be naught. So that's how I get my first equation over here. So V naught is plus I into R3. But what is I? I is R3 over RT plus R4. So we can write the equation as V naught is equal to V plus V into R3 all divided by R4. Or I can take the V common and get equation 3. So if I take the V common, then V naught is V into 1 plus R3 over R3 plus R4. Or you can write it in the form of 4, whereby you make the common denominator to be equal to RT plus R4. So you get equation 4, but equation 3 and 4 are just the same things. Okay. Now, let's consider this current, which is, I'll be calling it IREF. I hope you've come across this circuit over here. This circuit comprising of op-amp A3, Zener diode, and R5. So this circuit is actually one of the circuits we use to generate a constant current source. So if you have a Zener diode, connected to plus VCC, it means we drop a voltage from here to here, which is equal to Vz. Remember, Zener diodes operate when they're reverse biased. Now, from the property of the op-amp, if the positive input is at Vz, it means the minus input is also at Vz. So the potential between here and here is also equal to Vz. And therefore the current across, therefore the voltage drop across R5 is Vz, and therefore the current passing through R5, if I call it, say I, let's call it IR5, will just be equal to Vz divided by R5. And this current is almost the same current that passes through here, through the collector, if the current gain of the transistor is high. Because the current ratio between the emitter and collector is IE is beta plus 1 into IB. So in this case, the current that passes through the collector, I have not named the transistor. How many transistors? We've got 3 transistors. So let's call it Q3. So the current that passes through the collector of Q3 is just Vz divided by R5. Okay, and that current is not a function of the supply voltage. That current is fixed. Its value is just dependent on the value of Vz, the breakdown voltage of the Zener, and R5. So that's why we call it a reference current. So in my analysis, I think I'm calling it IRF. So that current will be equal to the current that goes through the vector of Q2. So this will be equal to IC2. Could be equal to the collector current of IC2. Of course, we make a slight assumption here that the Q2 has got a high current gain. So the current passing through its base to bias it is negligible. Otherwise, if you have to look at it very, very critically, that current IRF, part of it divides to the collector of Q2 and part of it required to bias the transistor, but that's negligible. Okay. So this now the important thing over here, unlike in the previous circuit that we used, that current was maybe some Vref minus V1 all divided by maybe some R2 or something in the previous class. I don't have it here. I've edited. It's not in this page, so I can't show you. But we've done it before. Okay, so now we can go back to analysis. So the reference current, IRF, I'm just calling it Vz divided by R5. And if HFE of Q2 greater than 1, i.e. IB can be considered to be 0, which is the bias current, of A2. I think I should also include the bias current of Q2. Q2 and A2. So because if you look at this circuit, some current will go this way, some will go this way, and some will be necessary for the biasing of the op amp, which is almost negligible. For the bias op amp is picoamperes. So that's why we can say that. So once we know that, now we can apply KVL to loop ABC. KVL to loop ABC. Let me just rub some of this to make it neater. So if A is not very clear in your laptop, the base is point A, the emitter point B, and this point is point C. So if we start at point A, we have to drop VBE of Q1, and then we add VBE of Q2, and that will be equal to the voltage at point C, which is the same as the voltage V, the same as this voltage V over here. Okay, so now we can move very quickly now. So I applied KVL to loop ABC. So we start minus VB1 plus VB2 is equal to V. Then for my Eber-Mohs current relations for the two transistors, we know that IC1 is not 1 e to the VB1 divided by neta VT minus 1, which can be approximated to I not 1 e to the VB1 over neta VT. And if we arrange, maybe I'd call it 8B. Somebody's trying to enter, but I can't see him now. So if you are his friend, he's going to complain. Tell him I'm using full screen presentation, so I can't see him. So from 8, we can go to 8B. Let's call this one 8B. 8B. So 8B is IC1. So if you divide I not 1 left-hand side, right-hand side of 8B, you'll get this 8C, which you can call here. This is, you can call that one 8C. Then take natural logs of left-hand side and right-hand side. Of 8C, we'll get 9. So you get natural log IC1 I not 1 is equal to VB1 over neta VT. Then we can solve for VBE1 from 9. We multiply right-hand side, left-hand side of 9 by neta VT. We get 10. So we've got the relationship between the collector currents and the VBEs of the transistor. So we can apply 10 to the second transistor, and we get equation 11. So similarly, we can get 11. We just substitute. Then we substitute these results. We substitute these results in our this equation over here, equation 7, which is minus VBE1 plus VBE2 is equal to V. But VB1 is 10, VB2 is 11. So minus VBE1. Let's go back again. We have minus VB1 plus VB2 is equal to V equation 7. So I think the minus sign is missing here in minus VBE1 plus VBE2. So there's a minus sign missing there. And it should be okay, not time for editing. No. So there should be a minus, and B2 should equal to V. The so the positive side, IC2 over IC1 remains the same. Then invert the IC1 over I01. So that's how we get this other term in the bracket. Now, if the transistors are matched, then the I01s and I02s will cancel. So 13 becomes 14 without the I01s. Now we want the equation to be in this form. We'll reciprocate whatever is in the inner bracket of the natural log. We put a minus sign outside because we want it in this form over here. So we get V is equal to minus delta VT, natural log IC1 over IC2. So remember, in our first equation, if we know V, we know the output. Now we got to determine, in fact, I've just written the result here. Remember, our result was V naught is all of this. And there should be a bracket there. So from 15, we've gotten V, but we've got to find out what is IC1 and IC2. So I've got 16 is just, let's call this one 15B. And now if I substitute in 15B for V, so V, I can get it from 15 over here, then I'll get this equation 16. Because there's supposed to be an outside bracket here. So now I've got to find out what is IC1, IC2 in terms of the circuits. Now IC1 is the current that flows through the first transistor. So this is our circuit. This is our circuit. So if you to clean it a bit. So the collector current, IC1. This current here is IC1. And this current over here is IC2. So IC1, if you look at A1, the input of the op-amp A1 is grounded to resistance R. The minus input of the op-amp A1 is a virtual R. So IC1 is this current over here. And it must have come from here. So IC1 is nothing but VS. over R1. Because this point over here at the minus input of A1 is a virtual earth. And IC2, we already computed it. IC2 is just simply this one. IC2 is just simply that one. It's just VZ divided by R5. So we substitute that in this equation 16. IC1 we got over here is just VS over R1. IC2 is the same as IRF, which is VZ over R5. So if you substitute this result in 16, you get that V0 now brought the RT plus R4 plus R3 all divided by RT plus R4 in front. The minus sign remains, so you get neta VT natural log VS over R1 for C1, and IC2 is VZ over R5, so you invert in the bracket. So you get the result as equation 17. So we can write this in the standard form. Oh, I didn't put in the standard form. Okay, we can just put it here. So this is of the form V0. This is the form V0 is equal to say some K1 natural log K2 into Vs. And call that equation 18. That's the standard form for a log amplifier. So this is the best performing log amp with very little approximation we can do. The null offsetting. So this is actually the best circuit to do in the lab. So you go to calibrate it, just as we did in the first before you can use it. So how do you calibrate this circuit? I'm not giving you this one in the notes because I'd given it earlier, a similar one earlier. So if you look at this circuit over here, so to calibrate this circuit, you short circuit Vs to the ground. And if you call this voltage at the output of A1, let's call it V1 dash. So to calibrate it, this circuit, step number one is to connect Vs to the ground. So you should circuit Vs to the ground. So if you're doing it to the lab, you should circuit the ground. Then V1 dash, the output of A1 should equal to 0. If it's not equal to 0, you vary the potentiometer P1 until the output is equal to 0. That should be your step one. Now, what should be your step two? Now, if you're doing these things in the lab, so from equation 17, so the steps in the calibration, if I was to write is here. So step one, set Vs equal to 0. So this should imply that V1 dash equal to 0. If not, vary P1 till V1 dash is equal to 0. Now, step two, set Vs to be equal to R1 Vz over R5. if you set this implies the natural log in the brackets. So instead of Vs now, in the brackets, so here we are using equation 17. So instead of Vs, now we'll have R1 Vz over R5 all divided by R1 R5 Vz. So this should equal to natural log of 1, and this term becomes 0. So step 2, you set. Check your circuit values for R1. The value of Z and R5. So in this second step, V0 should equal to 0. So if this term here in 17 is equal to 0, then V0 should be equal to 0. And if not, then you vary potentiometer P2 till V0 is equal to 0. And then you're ready to start your calibration. So this is it. So V0 is the overall output. The V0 we are talking about here is this one, V0. So the potentiometer P2 is this potentiometer here. So this is the best circuit actually to use in the labs. So it's called an improved matched transistor log amp with a constant current source. So a constant current source is this circuit over here, which comprises of Vz as in a diode, this resistance, the pump, PNP transistor, and R5. So any questions on this? So with that, we come to the end of the section of log amps. Remember, this is an important circuit which is used in analog computation. It's used in compressors. It's used in instruments that give log indications. It's used in analog computers. Now, the next important circuit is the anti-log amplifier, also called exponential amplifier. The anti-log amplifier is also called the exponential amplifier. So it's an amplifier whose output takes the form. Yes?
Concerning the log amplifiers,
Hey, just come again.
Hello.
Yes.
Okay. Looking into log amplifiers.
Yes.
I have a question. When we look at the Zen diode itself, and my question would be that what exactly determines the Zener voltage that we are supposed to use in these matched transistors, in these matched log amps? Is it the breakdown voltage that we use, the breakdown voltage of the diode, or what exactly is the rating, like the one that you would use in designing such amplifiers?
I don't know if I can you very clearly. determines the Zener voltage? The Zener voltage is, I mean, you have to select a specific voltage for your design, okay? Now that specific voltage depends on the current you want to pass over here. The current you want to pass over here, or the value of their constant current source. Otherwise, Zener voltages, sorry, Zeners are designed with respect to voltages and power. You can get Zeners of 2.7 volts, you can get Zeners of 3.3 volts, 4.7 volts, 5.1 volts. It goes all the way up to almost 100 volts. Okay. So you just got to make sure that the current passing over here, the current that is passing through this R5, the current passing through R5 is VZ. For example, if you have VCC supply, for example, since you're using op amps, okay, it means yes, the maximum VCC supply will be maybe 15 volts. That's at the limit. Normally, you don't operate the op amps at the limit. Okay, you leave us some safety factor in terms of the voltage. So maybe in your circuits in the lab, if you're designing this, your circuit will be using maybe plus minus 10 volts. So your VCC will be 10 volts. Okay. If this Zener that is designed for cannot be 10 volts, it will have to be less than 10 volts. Okay. Could be maybe 3.3, 4.7. Zeners don't come with voltages which are like, what can I say? Voltage which are like increments, say like a 1 volt. For example, you can get a 2 volt Zener, you can get a 3 volt Zener. Okay, but you can get maybe a 2.7 volt Zener, you can get a 3.3 volt Zener. Okay. So, for example, in this circuit, if I want 1 milliamp to flow, my RF current is 1 milliamp. Then it means if you go to the lab, maybe you'll get a 4.7 volts Zener. Or you can get maybe a 3.3 volts Zener. It's going by this equation over here. I see 2. It's going by this equation. It's going by this equation over here. Vz over R5. So for example, if R5 is 1K, if R5 is 1K, I use a 3 volt Zener, then the current that will be passing through that will be 3.3 divided by 1K, which is 3.3 milliamps. If I use 4K, it will be 4.7 milliamps. But normally, for log conformity, we want this current to be small. So it's good to have maybe a current of maybe 2 millivolts or less. Okay, so better still 1 milliamp. So if you're using 1 milliamp, then R5 should be approximately 3.3 kilo ohms. Okay, because we are using this equation, IC is I naught e to the minus VB over eta VT minus 1. Okay, that equation becomes more accurate the lower the current. So I hope I've answered your question. Okay, so like in this circuit, for example, I cannot use 10 amps as my constant current, so the circuit won't work. Okay, so I pick maybe a Zener of 3.3 volts, and then I use a resistor of, 33 ohms. Your circuit won't compute the log accurately. I've answered your question. We move on. Yes, switch on your mic.
Yes, yes.
Okay. Have you done this experiment in the lab? Have you done the experiment in the lab? Nobody's answering.
Yes.
You've done it? Did you get an answer? Okay, there's a lot of delay, let's move to the second topic today. So the next circuit is called the anti-log amplifier or the exponential amplifier. So this is an amplifier whose output, I don't know if I can increase. I think everybody can see. Whose output takes a form we notice some scalar K1 e to the some scalar K2 into Vs, where Vs is your input voltage. Okay, that's the standard form of representation of the output of this amplifier with respect to its input. But we can also rearrange this equation. If I divide this equation 1, and let's call this equation 1. So from equation 1, if I divide left-hand, right-hand side by K1, you can get it in form of 2. If I make reciprocal of K1 to be equal to K3, I can get in terms of 3. Then I take natural log of left-hand side of 3 and natural log of right-hand side of 3. I get 4. And then I take anti-log of 4, left-hand side, right-hand side. I'll get K3 V naught is natural log inverse K2 Vs. So solving for V naught in 5, I'll get V naught can be written as K4, where K4 is 1 over K3 into natural log inverse K2 Vs. So these are the two standard forms of representing an anti-log amplifier or an exponential amplifier. Of course, the most obvious form is that of equation 1. Okay, so any amplifier whose output takes the form of equation 1 or takes the form of equation 6 is an anti-log amplifier. So the applications of this one is an expansion of compressed signals. Expansion of compressed signals. In the earlier classes, I told you the need for compression of signals. So once you've compressed it, then you can expand it so that you remove the distortion that you introduced when you're compressing it. So they're used a lot in audio processing circuits, in analog computation also. So let's start with the most basic exponential amplifier or anti-log amplifier. So this is called the basic. It's called the basic diode anti-log amp. So once again, you're going to be using the property of the current through a diode and the voltage across the diode. So this is the most basic circuit. It's not practical, but it tells us how we can build a very basic anti-log amplifier. Now for this circuit, trying to get my pen stuck in the silo. Okay. Now for this circuit, we can write that V naught is I1. Since I'm not shown I1, that I was struggling to remove my pen. So if I call this current here through this feedback resistance, let's call it I1. Okay, so if current is flowing from the left to the right, so this side will be positive, this side will be negative across the resistor. Okay, so the positive side, and remember the positive input of the op-amp is connected to the earth. So it means the negative input to the op-amp is also connected to the earth virtually. So for the output, the top side is positive and this side is negative. So we can write that V naught is minus I1 into RF. I hope that is understood. Now I1 can only come from this part of the circuit. And this I1 is the same as the diode current, I diode. Now for a diode, Eber-Mole's current relation for a diode is given by this equation 2. I diode is I naught e to the V forward over neta Vt minus 1, which can be approximated to equal to I naught e to the Vf over neta Vt when the diode is conducting. And therefore, this I1 is just simply I diode, and I diode is given by this equation 3 over here. So we can write equation 1 in the form as V naught is just equal to minus I naught into the E Vf over neta Vt times Rf. But what is the voltage across the diode? The voltage across the diode, we normally call it Vf, or V forward bias of the diode, which is the same as our Vs over here. So we can substitute. Let's call this equation 4. So we can substitute in equation 4 instead of writing a Vf, we can put it as Vs. So we'll get, let's call this equation 5. So we get equation 5 that V naught is just minus I naught Rf e to the Vf over neta Vt. And this can be written in the standard form as V naught is some K1 e to the K2 into Vs, which is our standard equation for our exponential amplifier or anti-log amplifier. Now, the only thing to remember is that since for I1 to flow, Vs must be positive. So Vs must be positive. So I've written here for proper operation of the circuit, Vs must be greater than 0. And actually I should add some extra here, must be greater than 0. And but let's less than VD sat or VD saturation. Because for the diode, if you have to look at Vs for forward current of diode, the current of the diode normally flows something like that. And for silicon, the maximum is about 0.7 volts. For germanium is 0.2 volts. So this is the V forward or VD. Okay, so this circuit is only useful for computing the anti-log of voltages which are less than VD sat. In fact, as you approach VD sat of the diode, means 0.7 volts for silicon, 0.2 volts for germanium, the error start increasing a lot. And the error start increasing a lot. So it won't be very accurate. It won't be a very accurate computation. So this is just the first circuit, which is used to illustrate a very basic circuit known as the basic anti-log amp. So if you get to put a mathematical equation, and this is 0.7, 0.2 volts. So this circuit is only useful for computation of logs. Now, if you look again at this equation of 5 over there, you see the output voltage is a function of Y naught, which doubles for every 10-degree rise in temperature. So you're going to get lots of errors as the temperature increases. So we have to come up with a better circuit. So this circuit has got limitation. Number one, the input voltage should not be greater than VC set. Number two, the circuit is output is a function of I naught. And number three, you can add that this circuit only computes the logs for positive values of Vs. Because if you put a negative Vs at the input of this circuit over here, no current will flow. So no current will flow, and therefore there'll be no computation. So the improvement of this circuit with the basic anti-log amplifier to take care of the reverse saturation current I naught, we use what is known as the match diode anti-log amp. So this is the circuit of the match diode and anti-log amp. So here we are going to use two match diodes. And the voltage we want to compute its anti-log is Vs over here. With a constant current source, which gives a current IF over here. And the output is over here. So I've said that the above circuit is an improvement of the basic diode anti-log amplifier and does away with most of its limitations. The limitations of the former, i.e. variation of V naught with I naught and Vs less than Vd set. So let's show that this circuit can compute the anti-log of a single Vs at its input. So like apply KVL to loop ABC. So I'll start at point A, go to point B, and go to point C. Now the voltage here at this point here is V1. It might not be very clear in here. Just an arbitrary voltage to help us analyze the circuit. So A is ground, is virtual ground. Point A is virtual ground, which is input to, inverted the input to A2 because the positive side is grounded. So A is virtual ground. So I can go, the voltage drop across this second diode. I'm calling it VF2. So F there is the forward voltage. So this we can call as diode D1 and D2. Excuse me. So I start from A to B. I'm going to go against the voltage VF2. So I go minus VF2. Then I'm going to add the potential VF1. Should give me the potential at point C. And C is equal to the potential V1. So I can write this equation here, equation 1, minus VF2. F there stands for forward voltage. Plus VF1 of the first diode should equal to V1. Now for diode, we can write that I diode is approximately equal to I naught e to the Vf over eta Vt. I'm using some shortcuts here because we've done this equation many times. So if I divide left-hand side, right-hand side of maybe 2b, if I call this one 2b, I'll get this 2c. Let's call this one 2c. Should get I diode over I naught in general is e to the Vf over eta Vt. Now if I take natural log of 2c, left-hand side, right-hand side, and I'm doing too many steps in one. If I take natural log of 2c, you get natural log of I diode over I naught is equal to Vf divided by eta Vt. So if I'm to solve for Vf, I've got to multiply again by eta Vt, left-hand side, right-hand side. So I'll get 3. Okay, so this equation 3 is the general relationship between the voltage across the diode, or the forward voltage across the diode, with the current passing through that particular diode, for any general diode. Now let's apply 3 for the first diode. So if I apply 3 for the first diode, I just get eta Vt natural log instead of Id general. Now it will be If. It should be If1. It should be If1. Is equal to Vf1. And similarly, I can apply equation 3 for the second diode. I'll get eta Vt natural log. Is it F1 or I1? Let me see. In this circuit over here. Okay, it should just be understood that the current passing through the diode D1 is IF1 or I1. So we applied similarly for diode D2 over here. Same equation 3. All we substitute is for ID. You can call it I2 or IF2 over I02 is equal to Vf2. Now let's substitute equation 4, equation 5. In equation 1, equation 1 was the first equation where we applied KVL. Let's look at it. Equation 1 is here. Minus Vf2 plus Vf1 is equal to V1. So in equation 6, the first term is this one is minus Vf2. And Vf2 is our equation 5 over here. Plus Vf1 is equation 4 over here. I'm calling it IF or IF1. You can put it as IF1. Is equal to V1. Now let's simplify it. So take the common terms, eta Vt. We start with the positive term, which is IF1 over I01. So it is this IF or IF1 over I01, then we transpose the negative term of I2 divided by I02, so it becomes I02 divided by I2. So we get 7. So can apply that for matched diodes D1 and D2, I01 is equal to I02. So the I0s cancel and remain with the equation 8. So this IF, we'll just put as IF1 to avoid confusion. So equation 8 is neta Vt natural log IF1 over I2 is equal to V1. Now I want it in the form. I want the form in the natural log to be in terms of I2 over IF or IF1. So I remove the minus sign. I have to put a minus sign outside of 8. So I'll get minus neta Vt. It's called natural log I2 over IF1, or we could have called it, instead of IF1, I could have called it I1. The first diode is equal to V1. So I can simplify. 9 I divide the left-hand side of 9 with minus neta Vt. I'll get 10. I get natural log I2 over IF or IF1 is equal to minus V1 over neta Vt. Or taking the antilog for both sides of 10, you'll get e to the minus V1 over neta Vt is I2 over I1. Excuse me. Or I can write that IF1 e to the minus neta V1 over neta Vt is equal to I2 12. So now we've done all the hard work. So now we've got to look at the circuit and find out what is IF1, what is I2 according to the circuit, and what is V1 according to the circuit. So V1, let's go back to the circuit. So V1 is this voltage over here. V1 is just formed by this potential divider comprising of R2 and R1. So V1 is just Vs into R1 over R1 and I2. IF1 is the current that passes through this diode. So from this circuit over here, this is just equal to Vs R1 over R1 plus R2. Then we go to find out this current over here. We are calling IF1. So this current is just equal to our IF, which is from our constant current source. Okay, then we go to find out V0. Now V0, this is this input of A2. It's connected to the earth, the positive side. So this is connected to the earth. So the voltage drop across this is actually V0. So V0 is just simply because if this current I2 is this current passing through this diode here. So the positive side of the resistor, sorry, the right hand side of the resistor will be positive, which would correspond to the positive voltage. So the drop across this resistor is equal to our V0, which is just equal to I2 into R3. So we found the unknowns in terms of the circuit parameters. We found V1, we found IF1, we found, we can find I2. So I2 is just V0. And this also implies that I2 is just V0 divided by R3. So you put this in the final equation. So V1 is just Vs R1 plus R2. I2 is V0 over R3. So if we substitute that in equation 12, which we derived earlier on, we get IF e to the minus Vs R3 all divided by neta Vt into R1 plus R2 is equal to V0 over R3. This was supposed to be our I2. You can see it here. I2 over here. So making V0 the subject from 14 to 15. Let's put V0 on the left-hand side and then cross multiply by R3. So we'll get 15. So we'll get V0 is R3, IF exponent minus Vs R1 all divided by neta Vt into R1 plus R2. And this takes the standard form that we know, that V0 is some scalar K1 into K2 Vs. So the scalar K2 will be minus Vs over neta Vt into brackets R1 plus R2. So this circuit can perform anti-log computation or exponential computation. Now, if you look at equation 13, look at equation 15 over here. Look at equation 15. You see that the circuit is still a function of V0. Remember V0, it's still a function of Vt. And Vt is dependent on the absolute temperature. Vt is Kt divided by Q. And for practical circuits, the op-amp, or for practical circuits, for practical op-amps, the circuit still needs to deal with offsets, i.e., we need null offsetting potentiometers. So if you look at this circuit over here, this circuit, there's no null offsetting potentiometers. So effects of input offset voltages are going to affect the circuit so much. So it's not a practical circuit. So these are the limitations of this circuit. So we need an improvement of this circuit. So the improvement of the matched diode anti-log amplifier is the matched transistor anti-log amplifier. So in the transistor, we are using the diodes of the base emitter junctions, which operate at a lower current than that of the forward current of the diodes. So there'll be more accurate computation or more accurate log conformity. So this is the circuit. So in this circuit now, you can see we have null offsetting circuit comprising of potentiometer. I've not named the potentiometers, but you can see the potentiometer. Let's call this one P1. We're going to have potentiometer here, P2. So let's go quickly and show that this circuit is going to give better performance than the earlier one. So already we have the null offsetting circuits. And number two, we are using the base emitter junction diodes. So the current flowing through the base emitter diode is much, much less. So there'll be better conformity to the Haber-Maltz equation. So to analyze this circuit, I'll go as per my notes over here. Let's apply KVL to loop ABC So I'll set at the base of Q2 here and end up at point C over here. So point C is the same as this voltage V1. It may not be clear. So this voltage here, I'm calling it V1. So if I start at the A, I'll go minus VBE2 plus VBE1 is equal to V1. So this is my first equation over here, minus VB2 plus VB1 so that. So next we determine VB1 and VB2 from Eber-Moll's relation, which we've already done. So I'll just put the final result over here, which we found out. You get that VB1 is neta VT natural log IC1 over I01. VB2 is neta VT natural log IC2 over I02. So if you substitute results 2 and 3 in 1, you're going to get this C minus VB2. So this first term in equation 2 is minus VB2 plus VB1 is equal to V. Let's simplify it. Let's collect common terms together. Get neta VT common, natural log. So the positive in the natural log is IC1 over I01. The negative is IC2 over I02. So you invert it and put it inside the natural log. So the IC2 over I02 becomes I02 over IC2. And for my transistors, I01, I02 in 5 will cancel. So I'll just remain with in the natural log IC1 over IC2. But we want it in the form of IC2 over IC1. So we put the negative sign outside and we get 7. And then we arrange 7. Let's divide left-hand side of 7, right-hand side of 7 by minus neta VT. Then you'll get natural log IC2. IC1 is equal to minus V1 over neta VT. That's how we get 8. Take anti-log, left-hand side, right-hand side of 8. You'll get, and you rearrange it. What was on the right-hand side of 8, I put to the left. So I'll get e to the V1 over neta VT is equal to IC2 over IC1 multiply 9 left-hand side, right-hand side with IC1. So that you remain with IC2 only at the right-hand side. So you get equation 10. So now you got to find what is the value of V1, what's the value of IC1, and what's the value of IC2. So let's go to the circuit and find out what is IC1, what is IC2, what is V1. So from the circuit here, so if you look at this circuit over here, V1 is just formed by the potential divider. So you get V1 is just Vs into R3 over, I don't know, this 29.5K. I don't know what I've used. I maybe I've used it as R4. I don't know. Let's put it at R4. That's R3. Well, this R4 over here is this 29.5K. This resistance here. Okay. So next, you got to find out from this circuit, what is IC1? Here's where the assumption comes in. IC1 is the current that flows through this collector here, or the first transistor. Now, if the, let's call, I've not named the amplifiers, let's call this one A1 and let's call this one A2. Now, life would have been very easy if the positive input of A1 was grounded, but it is not grounded. So, IC1 will be equal to VR minus V1 over R2. Now, for the sake of analysis, because you can see that the potential divider formed by R3 and R4, the 29.5K, is such that the voltage V1 is approximately 0.5 divided by 30 times Vs. So we'll assume it to be very small. We'll assume for this analysis, in the next circuit, we'll see how to improve it. We'll assume that V1 is less than VR. So we can say that IC1 is approximately equal to VR over R2. So we've gotten V1, we've gotten IC1, and now we've got to get IC2. Now from the output circuit, if this V0, IC2 will be this current here. And I don't know what I've named this resistance in general. Let's assume it is, let's assume it's R4C. I don't know what I've used in the notes. So this current is IC2. So since the positive side of A2 is grounded, it means the minus sign, negative input of A2 is virtual earth. And therefore the drop across R4 is the same as the drop across V0. So we can write that V0 is just the same as IC2 into R4. So we can say that V0 over R4 is our IC2. So we'll check in the notes what I've used for this 10K resistor. Is it R4? Okay, so it's just very simple. So we determined V1, we determined IC2, we determined IC1. Let's go back to the notes. So from this equation 11, here's our V1. It's just Vs formed by the potential divider. So I'm calling that resistor R4. The resistor, which was 29.5K, I'm calling it R4. And then IC1 is VR minus V1 over R2, which said is approximately VR over R2. And the last relation was IC2, it's just V0 over R1. So I was calling this resistor here R1, not R4. I was calling this resistor this one R1. So this resistor, in my notes, I've called it R1. So we finished. So we've gotten V1 from 11, we've gotten IC1 from 12, we've gotten IC2 from that, from 13. So we just substitute everything in equation 10. So if we substitute in equation 10, and we transpose equation 10 so that the right-hand side becomes the left-hand side. So we'll start with the IC2 on the left-hand side. So IC2 is just 13. So you'll get V0 over R1 is VR over R2 exponent minus Vs over neta Vt into R3 over R3 plus R4. And you multiply left-hand side, right-hand side of 14 by R1. So you just remain with the V0 on the left-hand side. So you get V0 is equal to R1 divided by R2 into VR exponent minus Vs over neta Vt into R3 plus R4. And this can be written in the standard form, said that V0 is some K1, and so one is so big. Some K1 into e to the K2 Vs, which is our standard form for an exponential amplifier. Now, to use this circuit in the lab, you go to calibrate it. To use this circuit in the lab, you go to calibrate it. At least now we got the calibration components, the null offsetting resistors, and potentiometers. So standard one, procedure number one is set Vs and Vr is equal to 0. Now in the notes that I've sent to you, there's some typing error here. Please go and include this one. In the notes I've given, I've just written set Vs is equal to 0. Okay, but you should set Vs and Vr equal to 0. Now if you look at this circuit over here, so once again, if you call this voltage, the output of this is A1, let's call this one A2. So if you ground this, it means you're setting Vs is equal to 0. And also you set Vr to be equal to 0. Yes, grounded. Then the voltage, if we call this one V1 dash, should be equal to 0 because the voltage going to, the difference voltage going to the input of A1 is 0. So the output is equal to 0. If it is not 0, then vary potentiometer P1. This is our potentiometer P1. This is a potentiometer P2. So you vary P1 until V1 dash is equal to 0. So that's step number one. Now, step number two, you want step number two is set Vs equal to 0 and monitor the output of A2. If you put your comma and write that this so if Vs is equal to 0 in this equation 15, e to the power 0 is equal to 1. So in step number two, we are setting Vs is equal to 0. This Vs over here we make it equal to 0. So in the exponent, you'll get e to the power 0. And e to the power 0 is equal to 1. So V naught should be just this part over here. V naught should be R1 over R2 into VR. My English is wrong over here. This should this should give V naught equal to this should give V naught should equal to R1 over 2 into VR. If not, vary P2 until V naught is that. So there's some editing problem here. And with that, we complete. So once you've calibrated, now you're ready to start the experiment. And I'm very sure none of you have been doing that in the labs. Very, very sure. So you've not been getting the correct answer. Okay, so the advantages of this circuit is that Vs can be greater than Vd. It should be Vd set. Should be greater than Vd set of the diode. Also, the diodes used are those of the base emitter junction of the transistor, which operate at a much lower current, hence conformity, hence it should be greater conformity. Greater conformity to the exponential relationship of the Eber-Mols model. And then finally, the output is independent on I naught, which doubles for every 10-degree rise in temperature. Now let's see how we can remove the dependence on Vt. Actually, what I've said, the disadvantage, this should come in the next page. So the disadvantage is that the output is still dependent on Vt. Remember, Vt is Kt divided by Q. Now, here's a circuit, which is an improvement of this circuit. So we'll do this one now very, very quickly. So this is actually a better circuit because you got diode protections. Remember, I'm sure you guys will be blowing lots of transistors in the lab. All these circuits we've done, Vs must be positive. Vs must be positive with respect to the ground. If you put a negative voltage here for Vs, And this transistor on the left here won't be fired bias, it will be off. And the output voltage V1 dash over here will go to a large negative voltage, which will destroy both these two transistors. So to prevent that, in this circuit over here, we put these protection diodes D1 and D2. So that if the emitter becomes more positive than the base, it's limited to the base emitter voltage is limited to the saturation voltage of the diode. So if it's silicon, it will be only 0.6 or 7 volts. So that's a function of these two diodes, D1 and D2. Okay, so let's see. Remember in the earlier circuit also we did a lot of approximations. So let's hope this time we don't do the approximations. For those of you forgotten, remember, oh, I've wrapped the equations. But the approximation was that this current that passes through R2 is VR minus V1 divided by R2. But V1 does not necessarily have to be 0. If it was 0, then this current through R2 would be so easy. It should just be VR divided by R2. But we had to make the approximation that for all regions of operation, V1, you know, is Vs into R3, all divided by R3 plus this 29.5K. So this is a much better circuit. So let's show that this can also compute the antilog. Now this RT here stands for a thermistor. So the value of the thermistor resistance is R0 into 1 plus alpha T, where alpha is the temperature coefficient of this resistor over here. And to analyze this circuit also, we use an arbitrary voltage V at the base of Q1 over here. These are Q1, Q2. This is just to help us analyze the circuit. So we can start. We can apply KVL. So given the notes over here, but let's go directly to the equation. Time is not with us. Let's apply KVL to loop A, B, C. It's not very clear in your thing. This is A, B, C is the base of Q1. So if I start at point A, which is grounded to the earth, get minus VBE2 plus VBE1 is equal to V. So that's my first equation over here. I can rearrange equation 1 and write it as VB1 minus VB2. And now to save time, we already know what VB1 and VB2 are in terms of Weber-Mols relation. VB1 is neta VT natural log IC1 over I01. VB2 is neta VT natural log IC2 over I02. So the equation is the first term minus the second term should equal to V. Get the common terms. Neta VT is common. And the positive term is IC1 over I01. So we invert the second term, which is IC2 over I02 to become I02 over IC1 in the natural bracket. And then we cancel I0 and I0 2. The transfer of match transistors Q1 and Q2. So we just remain with the equation 4, which is V is neta Vt natural log IC1 over IC2, but we want it in the form, the natural log wanted in the form of IC2 over IC1. So we put the negative sign outside. So we get V is minus neta Vt natural log IC2 over IC1. So let's divide. Let's call this one 4b. We call this one say 4b. And divide left hand side, right hand side by minus neta Vt. And then we put the natural log side on the left hand side, we get 5. So we get natural log IC2 by I01 is minus V all divided by neta Vt. Taking the anti-log of 5, left hand side, right hand side, you get e to the minus V over neta Vt is IC1 over IC2. And therefore, if you make IC2 the subject, you get IC1 e to the minus V over neta Vt is equal to IC2. So from 7, we're going to find out what is V, we're going to find out what is IC1, we're going to find out what is IC2. Now from the circuit, we can get V. Let's go to the circuit. This is the circuit. Let's get V over here in the circuit. Now this, if you start from the ground, you go to RT, you go to point V, go to R3. So the voltage at V is just a potential divider formed of RT and RT plus R3. So V is just VS. VS is our supply over here. It's a DC, it's not an AC, shown over here. So V is just VS into RT, all divided by R3, or all divided by RT plus R3. So we've gotten that one. So we can write it here, that V is just equal to VS into RT all over RT plus R3. So next we got to find out what is IC1. IC1 is this current that passes through here. So this current that goes to bias. So if you call this A1, the input op amp, this is earth, this is virtual earth. So if this is 0 potential, this is 0 volts. So the drop from VR to 0 volts is what is going to push the current through R2. So this is your IC1. So IC1 will just be the drop across R2, which is VR over R2. And next, finally, we got to find out what is IC2. So the input of A2 is a 0 potential, is what earth. So the minus sign is also, the minus input is also a 0 potential, virtual earth. So the drop across RL is the same as the drop across V0. So we can write that V0 is just the same as IC2 into RL. So of course, this implies that IC2 is just V0 divided by RL. So we got those three unknowns. So we can put them back in our equation. V, IC1, and you can see now there's no approximation. There's no approximation of either of the currents. So we finished, we reached equation 7, where we had to find IC1. You have to find V, you have to find IC2. So V, just Vs, RT, RT plus R3. IC1, just VR divided by R2, and IC2 is V0 over RL. So substitute that in equation 7. So we get V0 over RL is equal to VR over R2 exponent minus Vs over neta Vt into RT, R2 plus R3. And there's supposed to be a bracket inside there. Time is not with me, so I'll just draw it here. Same with this one. So from 9, we just multiply left-hand side, right-hand side with RL. So we remain with only V. V0 on the left-hand side, so we get V0 is RL, VR over R2 exponent minus Vs RT divided by neta Vt into brackets RT plus R3. And equation 10 can be written in the form V0 is equal to K1 is equal to K1 e to the K2 Vs, where K2, we're going to take all this term minus RT over neta Vt into brackets RT plus R3. So any questions on this? Any questions on this? Now there are some simple exercises. Now this exercise is for both log and anti-log. This is more of like what you do in the lab exercise. So you're told question 1 for the basic transistor log amp, the input resistance Ri is that 10K. I notice 10 to the minus 3 amps. Calculate V0 for each of the following input voltages. So Vs is 10 millivolts, 100 millivolts, 1 volt. Just to test to see if the circuits are computing the log. And you're told to comment on the results and repeat the same. So this is just bread and butter questions. And then also you should do this. I don't want you to do this, but this is an exercise. So this exercise to practice. So you go and practice. This will come in the CAT. And this also similar problems. So we come to the end of this section. So our next topic. What's happening? So any questions so far? Any questions so far? You can ask me. We've got some 5 minutes. I do want to set a new topic. The next topic is multipliers. Any questions? There's no questions. Or if people are not there. Oh, CR, Moses, CR, switch on your mic. Moses. Moses is not there. Okay, Lady CR, you are there. Switch on your mic.
Yes.
Are you people in class?
Yes, we are.
Moses was supposed to go and check our classroom in the tower. And you're supposed to tell me
He will
today.
confirm today.
Yeah, we were supposed to have started today, but we're not sure whether we're going to get a class or not, a room or not. Because he told me the class you're having before this one, the other students which come and use that room in AW, in the American wing. Please, can you call